Good morning. So today's topic will be MOS Inverter Analysis. So far we have covered briefly the technological aspects, the layout aspects of MOS inverters as well as bipolar, transistor plus and ICs. Today and maybe tomorrow's class I will quickly review that or just give a very brief account of the analytical part of this MOS inverters. Before you do so, let us first see that how the transistor or MOSFET behaves in the two regions. This is the output characteristics of a MOSFET. As you remember, the MOSFET has two distinct characteristic regions. One is called saturation, the other is non-saturation or linear region. And the two are divided by a parabolic or rather a power law relationship like this. So we have characteristics something like this. Maybe something like this. And if we are referring to nMOS, you note that the polarity of VDS is positive, means drain positive with respect to source and substrate. So this is positive. And ID is positive in the sense that the drain current enters into the drain, the conventional drain current. Electron current flows from source to drain, but the conventional current, drain current, enters into the drain. That's why it is also positive, according to our circuit sense. Then, the set of characteristics which you have drawn, these are for different values of gate bias or gate voltage, VGS. So VGS is varying for the different curves. If it is a depletion mode transistor, if it is a depletion mode in MOSFET, maybe this curve is for VGS is equal to 0 for depletion mode. Whereas for enhancement mode, operation, this may not be for VG is equal to, rather this curve is for this bottom one. The bottom one is for VGS is equal to 0 or a negative bias. 0 or a negative bias. In fact, 0 to VT, if VGS is from 0 volt to threshold voltage, the current characteristic will be nothing but there will be no current. Up to threshold voltage, the drain current is practically negligible. So we get the characteristic is coincident with the abscissa, the VDS axis. But then, in the case of depletion mode, this may be VGS for say -1 volt, -2 volt, -3 volt. On the other hand, this may be for VGS is equal to 1 volt, 2 volt, 3 volt. Is it 1 volt, 2 volt, 3 volt? I don't think so. It will be threshold plus. So I will write VT plus 1, VT plus 2, VT plus 3, and so on and so forth. Similarly, if I go on for this particular case, this may be for +1 volt, +2 volt, etc. In this case, +4 volt, VT plus 4 volt, and so on and so forth. In the first example, it is clear from here the threshold voltage, which is also called pinch-off voltage, is simply equal to minus 3 volt. Because you see that for VGS is equal to minus 3 volt, ID is 0 everywhere, up to minus 3 volt. As I am growing on increasing VGS, when VGS becomes minus 3 volt, the current ID drops to 0 at all drain biases. Of course, below the breakdown voltage. Above a certain VDS, as you remember, the curves go up quickly, and that is what is called the breakdown in the MOSFET. That happens when the drain substrate junction breaks. The drain substrate junction, there is a breakdown in that junction. Then you remember the curves all go up. But below that, the curves are almost horizontal, and that is why this region of characteristics is called saturation. And for the second transistor, is simply that threshold voltage is not a pinch-off voltage. It is an enhancement mode device. And in this particular example, I have not given any value for VT. But VT could be 3 volt or 1 volt. If VT is 1 volt, then these curves are called 2 volt, 3 volt, 4 volt, etc. For this particular example, of course, I have assumed that VT is equal to VP, that is minus 3 volt. For the other example, that is enhancement mode MOSFET, VT can be any value, but usually it is positive. Please remember that we are speaking of nMOS. We are discussing nMOS. Just the opposite polarities of gate bias, drain bias, and drain current will apply to a PMOS. For example, if it was PMOS, all these things will be the same, but the signs will revert. This will be plus 1, plus 2, plus 3, minus 1, minus 2, etc. And here also VDS will be negative. ID will be negative. Current will come out of the drain. VDS is negative. Actually, the polarity of the drain bias with respect to source is negative. For depletion mode, this is for 0 volt, but others plus 1, plus 2, plus typically. This is for typical. I am writing typical. Typically. And similarly for the enhancement mode also, VT is negative. Please remember, for PMOS, VT is negative, and these things will increase negatively. That means when all these plus signs have to be replaced by minus sign when we consider PMOS enhancement mode. So there should not be any confusion. The region at the left of this curve, you can shadow it by red region, is called linear region. Whereas the region on the right of this is clearly called saturation region. So carefully note that a MOSFET, the drain current in a MOSFET, for a particular value of VGS, initially rises linearly with VDS following Ohm's law. ID versus VDS is a linear relationship passing through the origin. But as VDS increases, there is deviation from linearity. The curves become sublinear. And from this point, or these points onward to the right, the curve saturate means the current becomes independent of the drain bias. And the line dividing the two regions, okay, at every point, the relationship is that at every point, please note that at every point, VGS minus VDS is equal to VT. Please remember, at each point, this relationship must be valid. That means the effective voltage between the gate and drain, or the effective voltage at the gate at the drain end must be equal to threshold voltage. And this is the point of pinch off. We say the channel gets pinched off at these points. Okay, so the physics of MOSFETs already was discussed, I think, I'm sure, in your devices program, and something I've also discussed earlier. Now, a transistor, when in linear or non-saturation region, also called triode region. The relationship between ID and VDS and VGS are something like this. It's something like this. Refer to this curve. Here you see that in the linear region, ID is a function of both drain voltage VDS and VGS. Am I correct? In the linear region, ID is a function of both VDS and VGS. When VGS is very small, the linear region offers a very small slope, means very high resistance. And when VGS is very high, of course I am speaking of enhancement mode device, even VGS is very high, then you see that in the linear region ID VDS relationship is very stiff. That means it offers a very low channel resistance. Okay? So you see that ID is a function of both VDS and VGS in the linear region, and that is the simplest, this is a simple or approximate relationship between ID and the ID, functional dependence of ID on VGS and VDS. You can see very easily that when VDS is very small compared to unity, then this term drops out, so ID is proportional to VDS. And the proportionality constant is a function of VGS. The higher is the value of VGS, this proportionality constant is higher, indicating higher conductance, less resistance. Okay? Similarly, when you consider the transistor in the MOSFET in saturation region, the relationship between ID and the voltages, again, is an approximate relation, is beta by 2. I'll speak about beta afterward, in multiplied by VGS minus VT whole square. You note that in the saturation region, I have assumed that the current is independent of VDS. So saturation region current is a function of VGS only. And the relationship shows a parabolic kind of thing, and which is reflected in this relationship. You see that ID is proportional to VGS minus VT whole square. When VGS up to, for values of VGS up to VT, the current is 0. But as VGS exceeds VT, the saturation current increases following a square law relationship. In the two relations, beta is a parameter, is given by a formula like this. In both the relations, beta is given by an expression like this, where epsilon OX is the dielectric constant, the total permittivity of the gate dielectric, gate oxide. Mu n is the electron mobility in the inversion layer. We are speaking of nMOS. Similarly, it will become mu p, whole mobility for PMOS. And TOX is the oxide or gate oxide thickness. So the suffix OX indicates oxide, the gate oxide or gate dielectric. Epsilon is a dielectric of total permittivity. It's not epsilon OX is actually relative dielectric constant multiplied by epsilon naught. Epsilon naught is a free space permittivity. And this is total permittivity. And TOX is a gate oxide thickness. Mu n is the electron mobility. And finally, a geometrical factor which was introduced in the last class. W is the width of the channel and L is the channel length. So please note that the parameter beta in both the relations is a function of the geometrical parameter W by L, and you can define from this relationship, for example, you can define self-conductance of the channel, which is delta ID delta VDS with VGS constant. You can define transconductance or mutual conductance, which is delta ID or del ID divided by del VGS with VDS constants. So you can easily conclude, therefore, that both the self-conductance of the channel conductance, and the mutual or transconductance are proportional to beta. The higher is the value of beta, more will be this conductance, either the self-conductance of the channel or mutual conductance. Noting down the expression for beta, we can therefore conclude the transistor will have a higher current gain, higher transconductance or mutual conductance if the W by L ratio is higher, if the carrier mobility is higher. For example, definitely nMOS will be superior to PMOS, electrons having higher mobility than holes. It is proportional to epsilon OX, the dielectric constant. So if you can use a dielectric of higher permittivity, I will benefit so far as transconductance is concerned, and inversely proportional to the gate oxide thickness. Thinner is the gate oxide. As you know, in the latest advanced VLSI, gate oxides are very thin. So one is expecting to achieve a very high transconductance in a small geometry. And apart from all these things, the ratio W by L is not the absolute value of W and absolute value of L. Rather, the ratio of W to L, that is a very, very important parameter to determine the value of beta, which is also related to the transconductance GM and the self-conductance GD of the channel. All right? So after this very brief introduction of the basic MOSFET, let us see that how we can analyze the MOS inverter. Let us start with NELS configuration. Our discussions will be all centered around N channel because that is most popular because of obvious reasons. So NELS means the load is in saturation. So our MOSFET inverter configuration, again I am making the mistake. MOS inverter configuration will be like this. Okay, so here you see that to ensure that this load transistor is in saturation, this is load transistor, load, and this is driver. What I have done, I have made VGS of this transistor 0. Gate and drain are shorted. All right? Now, let us denote the current through the load transistor as IDL suffix, whereas the current through the driver transistor as IDD. And because I have ensured that the load transistor is in saturation, so I'll have to use the saturation region expression for the current. So what is the value of ID? IDL I will again write, to differentiate between load and driver, I will put a suffix small l with beta divided by 2, and it is VGS of the load transistor minus VT of the load transistor whole square. And this can be written as beta L by 2. And what is VGSL? Is simply VDD minus VO. According to this voltage, here with respect to ground is VDD. So gate and drain voltage is the same. And at this point, the voltage is VO with respect to ground. So VGSL is nothing but simply VDD minus VO. And we shall assume that both the load and driver transistors have the same threshold voltage, because fabrication will be the same, oxide thickness will be the same, so we expect the threshold voltage to be the same. So I will simply write VT instead of writing L and D here, whole square. Now suppose I make VI 0. I make VI 0. In that case, we expect that driver will be off. Driver will be off. So naturally, IDL will be equal to 0. Because driver is getting the current through the load. If driver current is 0, then the load current must also be equal to 0. And therefore, by looking from this equation, which I call equation number 1, looking from this equation, you see that VO is simply equal to VDD minus VT. All right? And what is this? This is nothing but your VOH, or I have also used sometimes this notation, VO at one state. So when the output, when the output is in the high state, the voltage is not VDD, rather it is VDD minus VT. So this is a very important thing which I already mentioned in the last class, and this is a drawback of the NELS inverter. The logic swing is less. When the output goes to high, it does not go to VDD, rather it is VDD minus VT. This is an important thing to be remembered. Next, you again refer to this diagram. So as the current, here what is VI? VI is nothing but VGS of the driver transistor. When VI is 0, the driver transistor is off, and the corresponding characteristic we can also draw. As you are increasing VI, the characteristic, the set of characteristics of the driver transistor will be traversed. Transistor will be above VT, the transistor will be on, and then gradually it will become more and more conducting. And we can superimpose on that set of output characteristics the load line which is offered by this active load. Okay? So let us do that now. Let me first draw the VDS, which is nothing but VO for the driver, and this is the ID of the driver, and we shall assume that IDD, and that I shall write. So these are the driver characteristics. And as before, we can draw the set of characteristics say we can draw like this. Etc. Because driver is always enhancement mode, so naturally this one will apply for VGS less than equal to VT, and then this is for gradually increasing value of VGS. Maybe if VT is 1 volt, then 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, so on and so forth, typically. Therefore, it can be easily voltages like 2 volt, 4 volt, 6 volt, 8 volt, 10 volt, etc. typical, assuming VT is equal to 2 volt. But assuming VT is equal to, VT is equal to, so in this case, of course, I should have not written that like that, 2 volt, so it will be just added by 2 volt. So you can correct it, 2 plus 2, 2 plus 4, 2 plus 6, 2 plus 8, 2 plus 10, where VT is equal to 10 volt. And we can superimpose on this set of output characteristics the load line which is offered by the pull-up transistor or the load transistor, which may be something, it will not be a straight line compared to the resistive load. If you just remember the old things, there is a straight line passing through. This point is VCC of the transistor characteristic, and this point is VCC by RC or VCC plus divided by RE plus RC, whatever. But in this case, I am coming to that, and you will expect to get a curve something like this. And what will be the corresponding value here? What will be the corresponding value here when ID is equal to 0? We have already seen. Yeah, that is nothing but, so if I say that this is VDD, then this difference will be VT. So VDD minus VT, and then again the curve will rise and it will be a nonlinear curve, something like this. Okay? Now, you note that this, whatever I have plotted in the abscissa, is nothing but the output voltage. Our VDS of the driver is nothing but VO. So if you are in this part of the characteristics, when VO is large, so what will happen? If you are in this part of the characteristic, when VO is large, then what will happen? The driver is in saturation. Load is always a saturated transistor, that we have assumed. But when your VO is close to, in this part, that is when VO is large compared to some minimum value, that we shall find out afterward, the transistor will be in saturation. So I can write down now an expression like this: when your VO is large compared to something which I call VOL, or also equal to VO1, VO0, the low state output voltage, then the driver MOSFET is in saturation. And therefore, the current formula for the driver current will be like this, already given, which is equal to beta d by 2 into VGS minus VT whole square. So again I am writing VGS for driver minus VT for driver, but we have assumed the same, whole square, and that is equal to beta d by 2 into simply VI minus VT whole square. Because VGSD is nothing but VI. We have seen that. The driver gate source voltage is nothing but the input voltage. I call this equation, I think I have given the last equation, equation number 1, so I call it equation number 2. Now in the steady state, let me again refer to this. If I call this current as load current, IL, I capital L, then in the steady state, I capital L must be equal to 0. Am I correct? Because what is the kind of load it is facing? It's a capacitance, pure capacitance. So in the steady state, that capacitive current is 0. No question of any current flowing through the capacitor, because this is MOS capacitance with a very, very high leakage resistance of the order of tens of mega ohm. In fact, maybe 100 mega ohm also. Pure electrostatic device. Purely electrostatic device. Please remember, that is why MOSFET is so good from various application point of view. And therefore, IDL is equal to simply IDD. And therefore, equation 1 can be equated with equation 2. Left hand side, of course. Left hand side of equation 1 can be equated with left hand side, or rather right hand side. And right hand side of the equation 1 can be equated to the equation, right hand side of equation 2, and which ultimately gives you a simple relationship between the output voltage and input voltage, something like this. You can easily find out yourself. VO is simply given by VDD minus 1 minus root over beta R. I have already defined this particular parameter, VT minus root over beta R into beta I, VI, where beta R is already defined, which is the ratio of W by, it is nothing but beta D divided by beta L, and which is effectively W by L of driver divided by W by L of load. I'm sure why beta D by beta L is equal to this you have understood, because we have used the same gate oxide for making the two transistors. So the other parameters remaining the same. It is the geometrical parameter which is important, and beta ratio is nothing but the ratio of the W by L values of the driver to the load. And what you note? You find that when your output voltage is close to the high state voltage, one state voltage, the relationship between VO and VI is linear. The relationship between VO and VI is linear, and the corresponding gain involved is simply equal to root over minus beta. That I am coming afterward. So this equation, if I call it equation number 3, is valid. 3 is valid for what condition? I am assuming that VI minus VO is less than equal to VT. actually VD, this is missing the thing. Now, high means basically it comes from here. I'm assuming that VDS of driver minus VGS of driver should be greater than equal to threshold voltage in order to ensure the saturation region of the driver transistor, because that otherwise this is not valid. I have to keep the driver in saturation, then only it is. And this is what is VDSD, is nothing but VO. And what is VGSD is nothing but VI and threshold. So ultimately we get this relationship out of it. Or effectively we can write it as like this, or VO is simply greater than equal to VI minus VT. VO is simply greater than equal to VI minus VT.
VO we are assuming to be in high state.
Just a minute. We are assuming that the drain bias minus this is for the saturation. We want to keep this driver transistor in saturation. So what I have to do for that? I have to make this condition that VGS minus V0 should be, yeah. So it will be just the opposite. I have written in the opposite fashion. So ultimately it must be like this. Sorry, this must be corrected. Your VGS minus VGS minus VDS should be. I think it is okay. We are writing that VDS minus VGS is greater than equal to VT.
Then VI plus VT. VO should be greater than VI because VGS is VI.
Yeah. So let us correct it like this. Yes.
VI minus VT.
Just a minute. VI minus. It has been written VI minus VGS minus VT less than. I think this is all right.
Should be VO minus VI should be equal to VT.
VI minus V2, so that is the same thing.
Minus VT.
That's all right. So you correct it. You are saying that input voltage VGS minus VG, the sign is the same thing. If you want that in linear region, then this must exceed in, I think this is all right. Then VDS minus VGS is greater than VGS, huh? Let me think about it. Our actually the gate voltage minus drain voltage at that end should be kept. It will be. Yeah. You are right. So you are saying that it will be.
VO minus VI greater than equal to VT.
VO minus VI. So actually this one is same thing. This one second equation. Yeah. This is, you're right. So finally, we have to ensure that VO is greater than equal to VI plus VT. You are right. That's right. So for this is the, and at the same time you see that your VI must be greater than equal to VT. That is important. Both conditions have to be satisfied. Input voltage must be above threshold voltage, otherwise it will not work. The transistor will not work, will not be in the on state, conducting state, and ultimately the VO. That is, these are two conditions must be satisfied. And from using this equation number 3, we can find out a relationship between VO and VI, which is clearly a linear relation in this particular case. Okay? Now, if we consider now the other situation when VO is less than equal to VI plus VT. All right? Then the driver will pass into linear region. So if this particular, the other criterion is satisfied, the driver will go into the linear region, and in that case I have to use that driver current expression valid for the linear region. So you please check your expression. So IDD will be equal to beta D by 2 into VGS minus V, that means VI minus VT, into VDS, that means VO, minus VDS squared, that means VO squared, and that is equal to ideal. Ideal equation already given. So equate them and get a relationship between the input and output. Ultimately, if you do that, after some manipulation, what we get? We get a relationship between the output and input, so-called the transfer relationship. And that comes in this particular form, which is like this. Where U and W are the normalized output and input voltages. What is U? U is simply equal to you have defined U as VO divided by VOH. That means VO divided by VDD minus VT. And input is W is given by VI minus VT divided by VOH. That means same thing as this one, VI minus VT divided by VDD minus VT. So you see that in the second case, when the transistor, the output transistor, the driver transistor goes into the linear region, passes into the linear region, the relationship is not that simple. Is it so simple? It's not so simple. It is now a quadratic equation. Whereas in the other case, it was a simple linear equation. It is a quadratic equation. And you know that you have to solve this quadratic equation. You see the equation is like the U square, then there is W, the coefficient W is there. So you have to find out the expression for the root of this equation, which will give you how U depends on W. That means how output voltage depends on the input voltage. It is now a simple task because it is a little bit complicated. We cannot do it that simply by in the form of that is what is normally advocated for this. If you are interested, you can write a very small computer program to obtain the input-output characteristics of the MOSFET over the entire range. I think I can give it as a problem to you. Why don't you note down some typical values for this? Please note down. So take it as a problem, as a home assignment. Plot the transfer characteristics of an NELS inverter. Plot the transfer characteristics of an NELS inverter with the following specifications. VDD is equal to 5 volt. Let me repeat, VDD is equal to 5 volt, comma, VT, the threshold voltage is 1.5 volt, and repeat calculations for two values of beta R. Beta R is equal to 5 and beta R is equal to 50. Do you need any extra information or any extra specification for this solving this problem? I don't think so, because I have specified the value of the threshold voltage and I have given the value of the VDD, and then I have asked you to repeat the same plots. That means you do two plots, one for beta ratio is equal to 5, the other for beta ratio is equal to 50. Now suppose if you are interested in determining, you have already got the value of VOH, but suppose I am now interested to determine the value of VOL. What to do? You know that VO is equal to VOL or VO0 if VI is equal to VOH, and that means that is equal to VDD minus VT, correct? Now you have already got an expression equating U and W, that is output voltage and input voltage. So in that input voltage you substitute the expression for, substitute VI is equal to VDD minus VT, and thus obtain the value of VO, which is nothing but your VOL. Am I correct? So take it as a problem. So this is the second problem. Find is a problem. Find VOL. So simple hint is this: if VI is equal to VOH, then VO is equal to VOL. So find out from that equation the expression for VOL. Alright? Then suppose I want to know that these two equations, over which, what is the boundary border, what are the corresponding values of input and output voltages for which the two equations will be valid. Two output input relationship will be valid. How to determine that? How to determine the boundary between, that is the values of VI and VO, between which, you know, that around which these two, that one equation where I have assumed that the divert transistor is in saturation, the other equation we have assumed the divert transistor is in linear region. So there must be some border between the two. And what is the corresponding VI and VO value? How to determine that? You simply substitute that condition that, so by doing that you prove that the border between the two regions is given by something like this: VI is equal to VDD plus root over beta R into VT divided by 1 plus root over beta R, and the corresponding VO is equal to VOH divided by 1 plus root over beta R. As we shall see, that this is a very important thing. To obtain the shape, the position, to adjust the noise margins of the MOSFET, these two equations are very important. You see that they are very much dependent on the value of beta R. You note that if beta R very high, then VO, the border between this thing, will be at a much lower VO. At the same time, same thing is repeated for VI. So by adjusting beta R, we can make a proper design of the MOS inverter so that the noise margins for the low state and high state, they are maximized and both of them have similar value, very close value. You have to maximize them. At the same time, you have to see that they have of the same order. Both of them should have, otherwise the characteristics will be highly non-asymmetric. It must be symmetric around the middle of the input voltage range. So that we shall see. So that is what I am just requesting you to do. The next class, you just do the two plots. Make the two plots, and then you can adjust the value of beta as well as threshold voltage. You can play with it. You can just do something, because you are writing a computer program. Here you can give any value of Vt, you can give any value of beta R. So adjust beta R and Vt such that the inverter is optimum from the point of view of noise margins. So again, this is a part of the problem. Optimize calculations by adjusting the values of Vt and beta R to achieve very high or as high as possible values of the noise margins. I have defined the noise margins in the last class. Okay? So it will be a pure computational problem. Thank you very much.